All right, welcome everyone to this life science stream from the Wolfram Institute. It's a pleasure to have Nick, Jonathan, and Uti with us today. We're going to be developing the ideas that we discussed last week on infrageometry and the new developments that came up that we encountered when thinking about the algebra of vector fields and trying to make sense of these discrete finite difference operators and how we operate them and how we do calculus with them. So it might be actually one of the slogans for today. I thought would be that we can actually recover infra-calculus in our context in a more proper sense. I think that we are identifying what that can mean in a very specific way when we tackle this idea of the general rewriting approach to operations and so on. But before we go on the sort of broader discussion and this concept that we came up with last week of edges as places, maybe we can hear from Uti about any updates on the algebra front or the geometric interpretation of finite difference operators and the stuff that you've heard from him in the past couple of weeks. So please take it away.
Sure. So, I mean, our explanation of weighted derivations was I wouldn't say it was very useful in the graph case, because in the graph case, it reduces to kind of trivial statements. I mean, essentially, the idea is as the weight W goes to 0, the expectation is that you get a derivation. But in my explanation of weighted derivations, that's not always true. It turns out that, okay, so essentially, just some context. A weighted derivation is the property that's obeyed by functions or like these difference operators on these finite difference operators we defined. And as W goes to 0, we get the normal Leibniz rule. And so the idea is that you can prove that if given an algebra homomorphism, you can recover a weighted derivation. It's like, and all weighted derivations are of this form. Like all weighted derivations come from some algebra homomorphism. And so the idea is that if the algebra homomorphism itself depends on W, then as you take W goes to 0, the algebra homomorphism will also tend to 0. And then the operation that gives you a weighted derivation, the expression should tend to like a derivation. So it only holds true in certain algebras, that given an algebra homomorphism, which is like in terms of W, which is some sort of a perturbation, as W goes to 0, it will give you a derivation. And it holds precisely for those algebras which are like smooth in a sense, which like where you can expand things in a Taylor series. So the set of, let's say, the smooth functions on a manifold, you can always expand any smooth function on a manifold in terms of in terms of its Taylor series. And so the operation of taking W goes to 0 is, you're not essentially taking a limit, you're just taking the first order term of the perturbation, and the first order term of that perturbation is the derivations. It's df by dx, right? And so you can generalize that by saying that, hey, if I have an algebra A, then a perturbation of that algebra is essentially like an algebra homomorphism from A to like the power series algebra over A, so that of the form A plus some function of A t plus function of A t square and so on and so forth. And so if the requirement that the first order term is a derivation is precisely the requirement that the entire power series, the phi that takes A to AT, is an algebra homomorphism. And so so I'm trying to explore that front right now, where, given algebra homomorphism in this form, when do they translate into like some analytic thing? Like, what's the property of the algebra that allows me to actually take the limit in an analytic sense, given its algebraic description? And so I can like share a couple of results about how this like is relevant to graphs in a sense, and maybe it will yield some interesting ideas. So
can I begin by asking a super naive question as someone who I haven't been following this as closely as I should, so this may be very stupid, but so all right.
Okay.
We have a K algebra and we have a we have a k derivation on that k algebra, and we know that forms, you know, the commutator of those derivations forms a Lie algebra, right? Now, in the case of weighted k derivations, they also form a Lie algebra when the weight is 0, because that's just a normal derivation, right? And you're effectively, what you're talking about at the moment, it sounds like, is, you know, what conditions do you have to have on the algebra for it to make sense for you to set the weight to 0, right?
Yeah, precisely.
So, okay, very basic question. Are there cases where even for non-zero weight, you still get a valid Lie algebra just because of some cancellation of those additional higher order terms? Or is that known to be impossible?
It's impossible because like it's not, so if you're essentially asking that is it possible to turn the set of weighted derivations where W like over like some weight W, is it possible to turn it into a Lie algebra? Then it's not possible to turn it into a Lie algebra because of the second order term.
But right, so the second order, there's no scenario, there's no like special case of an algebra and a particular algebra and a particular weight where those second order terms somehow cancel out.
No,
okay.
It's a very standard proof, but and that's no, it doesn't hold.
Are there any other algebraic, and this is, I guess, both to Uti and to Carlos and possibly Nick, but are there any other algebraic properties of derivations beyond just, you know, formation of a Lie algebra under a commutator that one might care about, which might persist for non-zero W?
Yeah, for sure. Like essentially we found like a formula that tells me that if I have two weighted derivations of W1 and W2, then like under some operation you get another weighted derivation of weight W1 times W2.
What is that operation?
Okay, I'll share my screen.
Yeah.
I
just show that. That was one of the results that I think got a bit overshadowed by the meeting with Stephen, because I don't think we had a meeting between that. I mean, the discovery of that and the meeting with Stephen. But
right,
it actually will be worth to discuss it briefly here, because the significance of that might, you know, push us into specific directions in the geometric analogy.
Okay. Yeah, it carries extremely, like it's a very nice correspondence to like graphs. It basically turns out that operation corresponds to like composition of vector fields.
Yeah.
Okay, so anyway, just as a recap, this is what a weighted derivation is, where W is in K. I need W to be in K. If I take W to be in A, I want it to be invertible. So that's like the only property I'm using over here. But for simplicity, I think it's fine to keep it in K. So this is a pretty elementary result, that if you have a K algebra and it's an algebra homomorphism, and then this is the weighted derivation, where this is the identity map. It's a purely computational result. And now you can go the reverse way by taking W on that side and then adding the identity to say that if you have a weighted derivation, then this is an algebra homomorphism. Again, just like a pure computational result. And so this tells me that all weighted derivations in algebra are of this form. They come from these algebra homomorphisms. Is there any comment now, or is everything fine now?
Well, no, I mean, this is, I think, what we saw in the meeting with Stephen, right?
Yeah.
Yeah. Okay.
Yeah.
Now this is the closed form thing I was talking about. You take a weighted derivation of this weight, and then another one of this weight, and then this is a weighted derivation of this weight. And so what is it, and how did I come up with this? It's very simple. If this is a weighted derivation, I know from this that it's an algebra homomorphism, and this is also an algebra homomorphism. So the derivation that actually corresponds to their composition is this. So like a standard, so the algebraic property is also like composition of these homomorphisms correspond to doing this with the derivations. Okay, then there are some results.
So let me comment. Let me comment briefly on that result. So that's a somewhat disconcerting result the first time that you see it, because it tells you that for weight different than 0, there's no distinction between derivations and algebra homomorphisms, which in a way is a very somehow uncomfortable fact, because if you're trying to interpret this geometrically, then suddenly your derivations lose their status as something infinitesimal, or something that is going to talk about dynamics locally and so on, right? Because, I mean, if you take this to heart and you apply it to the geometric case, all that this is telling you is that all the weighted derivations are finite flows on your space, right? And so I am not entirely convinced that this is the end of the story for weighted derivations, in the sense that you know, it might be that when you have a weighted derivation that is only partially defined, so you don't have such a global statement about all the, I mean, this one-to-one correspondence, you might still induce some local homomorphisms that don't glue up to a global homomorphism. So there might be something to be said about those structures still, but in any case, I think this result is somewhat disconcerting. I mean, I'm still not entirely sure how to digest, because I mean, on the face of it, it seems like you just basically drop the notion of weighted derivation because it's redundant, and you just stay with algebra homomorphisms, right?
Carlos, I mean, so yeah, you were right when you said that it's disconcerting, and you're right, it doesn't hold true for all algebras, as I previously said, but it does hold true for algebras that are smooth.
Yeah.
So it's a very trivial example. Consider a smooth manifold and the set of smooth functions on that manifold. Construct an algebra homomorphism from the set of smooth functions to the set of smooth functions that takes a function f and evaluate, and then the new function is the evaluation at some perturbation from, so like it's f goes to f prime, where f prime of x is f of x plus epsilon. So, and that is trivially an algebra homomorphism because it's just an evaluation function.
Where so when you say plus epsilon, you mean some
Yeah,
infinitesimal
like
diffeomorphism in the manifold.
yeah, so it's like this is the oops. So this, where this evaluated x is defined to be f of x plus like epsilon. So
Yeah.
let's say, I mean, let's deal with like functions over the real line.
Sure.
Like, so this is like well defined over there. Now this is an algebra homomorphism pretty clearly from the set of smooth functions over the real to the set of smooth functions over the real, because it's just evaluation. So phi of f plus g is f plus g evaluated at this, which is f evaluated this plus g. Okay, so it's an algebra homomorphism, but then we can easily get a derivation out of it by expanding this in a Taylor series. And so this is the derivation. The first order term is a derivation. And so it turns out that for smooth algebras, if you take a algebra homomorphism that's some sort of a perturbation, then since the algebra is smooth, you can expand it in a Taylor series, and the first order term will be a derivation because the original phi is an algebra homomorphism. So the idea is that if I have an algebra A, then I can construct this algebra, right? Now I can then forget about the analytic properties of functions of that algebra for a second and just consider like algebra homomorphisms from A to the power series algebra. And so it's very easy to prove that if you have an algebra homomorphism from here to here of this form, and so on, then phi 1 should be a derivation. Like it follows directly from the algebraic properties of how polynomials multiply. Now the question is, when can I go from an algebra homomorphism of this form to a derivation? Is that if the algebra is smooth, then this algebra homomorphism can actually be translated into an algebra homomorphism from the algebra to itself. Because since it is like in a sense analytic and smooth, I can literally just treat t to be like some small value in the algebra, or some thing in the algebra that will allow this to be well defined. And so then by definition, this is a derivation, and I've recovered that derivation from an algebra homomorphism from here. But by the smoothness property, this is an algebra homomorphism from the algebra to itself. And so for smooth algebras, there's this one-to-one correspondence. which I haven't proven yet. Sorry.
I think that's quite clear, but I suppose the concerning thing is, yes, okay, you can do this construction using the power series algebra in the smooth case. As far as I can tell, unless maybe you have proved this and I haven't seen it, there's no demonstration that you can't do something. Obviously you can't do this construction, but there's no demonstration that you can't do a construction in the non-smooth case. Is there?
I don't. I mean, let's say if you take like the set of functions, like set of two differentiable functions, let's say, from the reals to the reals, then like I don't think you can do this construction because
no, you obviously can't do this construction, but that's not the question. The question is whether it's whether you can induce an algebra homomorphism, whether you do ultimately have closure under composition.
Sorry, I don't understand the question. Like
you've proved that in the smooth case, you've demonstrated a construction, and you said, okay, this construction gives me an algebra homomorphism, and therefore I can have closure under composition of my weighted derivation, right? Yes. You then said that construction doesn't work in the non-smooth case, and it seems like you're implying that means that you can't, that you don't get that same property in the non-smooth case. But that doesn't
the closure under composition,
right?
That property. No, that property holds in all algebras, as I've proved over here.
And that you get an algebra homomorphism.
Yes.
So
no, the idea is that from an algebra homomorphism, how do I get to a derivation, not a weighted derivation, with like W is equal to 0. So that construction itself is specific to smooth algebras. It's not. That construction cannot be defined for non-smooth algebras.
So you provably can't get a W equals 0 derivation from composition of two W not equal to 0 derivations in a non-smooth algebra.
No, I mean, not the composition. Like you just can't even, given an algebra homomorphism, you cannot get the derivation itself in a non-smooth algebra. Like I don't see how the composition property is relevant over here. I'm talking about purely getting the derivation from an algebra homomorphism. Because I'm referring to this result.
Right. So why can't you do that?
Because if you have an algebra homomorphism phi, and let's say you want to, and this is a W derivation, so the idea should be to let W to 0, and so this operator should tend to a derivation. And so what does that mean? That means phi as W goes to 0 should reduce to the identity, right? Otherwise, this limit is not well defined. So that means that you need to have some phi, which is in a sense some power series over like W. But then the thing is that
why does that follow?
Because if I want this operator to go to 0 as W goes to 0, then
you want phi approaches the identity.
Yeah. And so ideally it should be of this form. Something W, something W squared, and so on, right? Now, the claim is that how do you get...
Hang on, why?
I mean...
There are non-analytic functions that still go to 0.
Right. But like is this an operator? So like you should be able to do... I mean, here like the idea of taking the limit of an operator is not well defined. So I'm not saying that it should be of this form. I'm saying that since I don't have access to the analytic properties of the algebra, I'm saying that if there exists a phi which is of this form where I treat W to be some T instead of an actual W inside the field, I can construct this. But in that case, like there's no way of turning that T into a W so that it becomes an algebra homomorphism from A to itself, like to A, not instead of A of T. It's easy to obtain algebra homomorphism from A to A, the power series, and get a derivation. But for
I understand that.
Yeah,
and I understand that construction doesn't work in this case. But
yeah,
we know there are cases where you don't have an analytic function, but by taking distributional limits, there's still a definite sense in which you can say it goes to 0 under some condition.
Okay, I mean,
and so I'm asking what you're asserting that isn't true in this case, and I'm just wondering how we know that.
Like I don't have a concrete proof of this, but like from intuition, it seems pretty like trivial that the algebra we have has to have like some standard properties which allow me to do this Taylor series expansion. Like I don't have to like consider those extra cases.
But I don't understand why that isn't circular. You're saying we have to assume that the algebra, in order for my intuition to work, I have to assume the algebra permits a Taylor series expansion, and therefore I proved it only works for smooth algebras. That
okay, sure.
I don't understand that argument.
No, I see the argument. Okay, sure. Maybe there is some, maybe not one-to-one, but maybe there's some specific algebra homomorphism that gives you a derivation in like a similar
I can certainly agree that there's a very clean and direct way of getting an algebra homomorphism in the smooth case.
Right, right.
I think I'm not as eager as you are to dismiss the possibility that there could be an analogous construction in the non-smooth case.
Okay, I mean, it certainly doesn't work. So, okay, I've only looked at trivial examples of non-smooth algebras, like the set of smooth functions up to like order n, differentiability n, and over there you cannot do this construction. Sure, I don't know if there are some other algebras whether this holds, but from the basic algebras like polynomial algebras, which are smooth and so on, there's, it's a very nice correspondence. So I feel like in the graph case, it would be nice to look at, it would be nice to basically say that, hey, start with the assumption that the set of smooth functions over this graph like is smooth, and we're only sampling the values of the function of like at those discrete points, and that gives a nice algebra structure to like the function itself, and there's a nice way of obtaining the limits of as the graph goes to infinity and so on. So yes, I have not considered the other case. I've only like shown one direction. So
okay, no, sorry, I'm
no, okay, that's a valid point. I haven't looked at those other examples.
I'm partially asking because what I guess, okay, in part I share, I suppose, Carlos's concern that it's like somehow we've lost most or all of the analytic structure when we pass to this kind of method of argument. But the other thing is that, for me at least, and maybe, I don't know, maybe this will degenerate into a more open-ended discussion at some point, but it's not clear when we translate to the graph case, it's not clear how those smoothness properties will translate over. Like I at least have not yet seen what I consider to be a kind of satisfactory definition of what it means to be a CN function on a graph.
Yep.
Right. Yeah, that's true.
This is where we're going. Yes, this is exactly where we're going.
Okay, great.
Yes.
Sorry, then let me not interrupt.
No. But okay, we're going there. But this is a somewhat like a detour in a way, because to voice my concern about this result, which looks clean and clear. So in the smooth setting, right, there's this result that tells you that if you have a commutative algebra homomorphism for the algebra of functions, the commutative algebra of functions on that manifold, real valued functions on a real manifold, then that homomorphism must correspond to the pullback by some smooth map, some smooth endomap of that space, right? So this result applied to the smooth context basically tells you that weighted derivations in the smooth case reduce to endomaps. So something that we knew that such maps provided examples of weighted derivations because they are finite difference operators, right? You just need to specify a smooth endomap, and you get a map from smooth functions to smooth functions, and they behave precisely like finite differences. So they are weighted derivations, as we know. So this result, in a way, will imply that there's nothing in weighted derivations that is not just in endomaps, right? So, I mean, I wanted to bring it up in the stream. It's not directly related to the graph stuff that what is a CN function and so on, because that's the interesting stuff in my opinion. That's where the edges as places came from, by the way.
Okay, great.
But this begs the question, in my opinion, that if this is crystal clear, that we've shown that weighted derivations in the smooth case reduce to smooth maps of the space, smooth endomorphisms of the manifold, then it's pretty safe to say there's nothing there, right? In the smooth case, we're not going to learn anything by looking at weighted derivations, because, I mean, there might be something interesting to try and work with the finite difference operators as by using the weight, or using the the weighted Leibniz rule or something to illustrate something specific. But it seems to me that there's not going to be a sort of an uncharted territory of mathematical structure that we haven't seen before, if we in fact have a one-to-one correspondence with smooth endomaps, right? I mean, so that was the sort of uncomfortable nature of this result, that it, in some sense, diminishes the excitement of having found an algebraic structure for these things, because in the end, all you're doing is actually composing those endomaps. And in the discrete case, everything is even more clear, because it's like actually mapping edges, vertices to vertices, and everything is very nice. But yeah, I don't know what to make of this, because it's kind of a closed story at this point. It's like, yeah, you show that all the weighted derivations in the smooth case are in fact endomaps, and I don't know, it's a bit contentious. Yeah.
So I mean, derivations in the smooth case are endomaps.
No, weighted derivations.
Yeah, weighted derivations are endomaps even in non-smooth case. But derivations like w is equal to 0, they are endomaps in the smooth case.
They are not. They are. You can have a map. You can have this functorial. Is the derivative construction, right? It's the differential construction that takes you from one to the other. But you need the notion of an infinitesimal, right? So you need a
yes, you do.
one parameter subgroup, or whatever you want to, however you want to approach it. You need that.
But I still don't get why it's like unnecessary, because I feel like the most trivial example, or the most important example we should work out first is, like, I don't get what you mean by when you say that the smooth case is not like we won't learn anything from that, because I think it's still pretty relevant to figure out, like, what does it mean for a graph to grow, so that the set of functions on that graph also grow in like some appropriate way to approach like the set of smooth functions over some space, right? If like we should be able to answer that very basic question, like, how do I get the real numbers from like a graph? You define a set of smooth functions on a finite graph at endpoints, and then you grow them out.
Sure.
And then you grow them out in a way so that the functions themselves approach the set of smooth functions on a real number line. So,
but the problem is that with this algebraic approach, we're not heading there directly, at least, right? Because in this algebraic approach, you basically make assertions about the category that you're in. You say we are in this particular category of algebras, and we have homomorphisms of this kind, and then can you find some kind of functorial construction to these other category of algebras that you're interested in, and so on. But I mean, that's only going to give you some kind of background land to, or sort of territory to speak about your limits and so on, if you do construct them. But you're not going to be able, I mean, algebra itself is not going to tell you explicitly about whether you can take limits and things like that, right? You need to, I mean, you need to develop some sense of an analysis to do that, or specify what you want out of your limits in this case, right?
I mean, okay, maybe this is hopelessly optimistic, in which case let me know. But so, is there a possibility that, okay, so suppose we develop this formalism to the point where, given a graph, we can kind of algorithmically construct the category of smooth functions that whatever the discrete analog of smooth functions ends up being. We can construct that category. We get its algebraic properties. Then I suppose, given that we know that you get these endomaps in the smooth case for weighted derivations, then is there not an argument that Uti's kind of algebraic construction gives one a way of kind of quantifying how far away the functions you can define on that graph are from being kind of bona fide smooth functions?
I honestly don't see how that could work, because one of the points that we were going to make about this edges as places and how to understand continuity in the discrete case and so on is precisely that so far we've dealt with functions as vertex assignments of values, right? So we've assigned whatever a field value to a vertex, and we call it a day because we had reasonably intuitive notions going around, like finite difference operators and directional derivatives and things like that, that they kind of made sense at first approximation. But when you think about it more seriously, you realize that functions from vertices to a field cannot possibly be the actual set of functions that you want to consider as your candidate for the discrete analog of continuous functions or smooth functions, because I mean those are simply just set functions. There's no structure. They don't interact at all with the graphic structure, right? So in a way, it is to be expected that we. So let me put this into perspective. To me, it makes sense that we run into this kind of situation where we see that the definition is sort of obvious, that we are actually just doing endomaps and that we're mapping vertices to vertices, because we are looking at functions that are defined on a set. And yes, we are considering some graphic data to do local flows or finite difference operators or whatnot, or like tangent vectors and so on. But that's only sort of half of the story is graphic. The other half is still purely set theoretic based on the vertex set, right?
And also, I would argue that the graphic structure comes in when you define that one parameter subgroup, or however it is that you're defining the infinitesimals that OT needs to get the W equals 0 case.
Yeah.
And perhaps that's
so
right? I don't know.
Precisely. So so here's my intuition about how this should work. There is no point in me doing, like, at least I think there's no point in me exploring this algebra side of things if I can't define what it means to grow the graph to infinity. Because the set of smooth functions, let's say, so here's the intuition that I had. You have any graph which is discrete and you embed it in some like n-dimensional space. So assume you have a line graph, like a bunch of dots, right? And then you embed it in the real number line. And then you say, okay, what's the analog of the set of smooth functions on that line? For me, the first step, like the first obvious step to do, is to just consider the set of smooth functions on the real number line and interpolate it at the points at the line graph, right? But we know just from visual knowledge that we can literally draw any smooth function. Like we can make as many wiggles as we want, and the function can still be smooth. So the restriction of that the Taylor series expansion puts on these functions is not enough to give me any information about the set of functions on a graph. So in fact, I think it turns out that if you have any set map from a bunch of discrete points to the field, then in some limit it will approach to like a smooth function. Like in the discrete case, there's no way for me to say that, hey, this set map is a smooth function and this is not, because a smooth function can take arbitrary values extremely fast and can have high derivatives and so on. So if I can't define what it means to grow the graph, then as you said, Carlos, there's not a lot of interesting algebraic properties of set functions can have. And also, if I look at sub-algebras of those functions over the graph, like they don't have any interesting properties.
Yeah.
So I can only do some meaningful exploration if I know what it means to grow the graph to like infinity.
Yeah, and I would say more. It's not just knowing to grow the graph. I was going one step before, which is given a graph, what does it mean to have a function that is continuous or placeholder continuous, candidate for continuous in the discrete sense, right? And then when you grow it, my intuition is that you want to preserve that property so that you are converging into, so a class of functions is converging into the class of functions that you know in the limit, and you can make some metric analogies, and you can actually take limits in a formal sense, in an analytical sense. But I was sort of preceding that step by saying, well, first of all, we need to know what it means for a function to be continuous, and maybe I should go ahead and do this brief motivation of what this edges places and this motivation for the continuous. I don't know if there was something, Uti, that you wanted to still present.
Not really. It's just, I don't know. Let me see. Yeah, so that was like cool result, that if I have two vector fields, then this is the corresponding weighted derivation. This is the corresponding weighted derivation. This correspond, and that operator that I told you guys about, that's the weighted derivation corresponding to the composition of the vector fields. So it's just like a neat result.
Wait, can you
Yeah, that's
explain that a little bit further? So what is a vector field? What is a vector field here?
a vector field is essentially, I viewed it as a function from the vertices to itself, where x of v is in the neighborhood of v.
Ah,
This is
okay,
like
okay,
a-
okay, 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 okay.
right.
So yeah, so
And
this is the
so
discrete case, yeah.
yeah, and
Right.
so this is a pretty easy result. If I have any vector field, so if I view this, then I can construct an algebra homomorphism from the set of functions that that takes a function and gives another set function that just evaluates which basically takes a vertex and evaluates it at the next point.
Sure.
So that's an algebra homomorphism. So this is like an evaluation function. So it's akin to like an infinitesimal
Yeah.
homomorphism in the smooth case where I'm just
Yeah.
evaluating the function at plus epsilon.
Yeah.
And then I try to define some things like Morse functions and so on. And there's this Oliver Nill has some interesting results about how that plays out, but I haven't seen those yet. Then given a vector field, Carlos, you basically define this operator, the finite difference operator, that takes a function and gives me another function, which is described by this, which it takes a function at the next point of the vector field, the point that the vector points to, and subtracts it from the original value, divides it by w. And then I prove this result, where this is the map, basically, which evaluates the function at the perturbation, the next edge, and it has this nice property. Then from this property, I deduce this property.
Yeah.
So that's it.
Yeah, that's nice. That's a nice. It's a nice packaging of the algebraic result in the finite graphic result. And that's nice. Yeah, that's cool. Okay, thanks very much. I think that actually thanks for showing that, Uti, because that I hadn't seen that final result, but that kind of keeps the ribbon on the sort of package of finite derivations, finite difference operators, and weighted derivations kind of story in the graphic case. So let me motivate let me see if I have a good drawing. I think because my stylus is still broken from my tablet, so unfortunately I can't properly draw. I think I mentioned this in the last live stream. If you ever get a Microsoft sort of Surface thing, never get the default stylus. It's terrible. It falls once in like 20 centimeter height and it's over. So let me maybe share just I'll just free draw on a canvas here.
On that, I can highly recommend the Galaxy S Pen, which I have dropped I don't know how many times from unbounded height, and it's still fine.
Okay, I'm actually going to go and shop for pens right after this. That's actually very useful. Okay, so let me just share this. Can you guys see this? No, actually you can, but the viewers can't. So let me just move it over here and try to share it again. Screen one. Yeah, you can see this, right?
Yeah, we can see it. I'm not sure if the viewers can.
Yeah, viewers can. I can just check.
Okay, perfect.
So anyway, I mean, this is the infrageometry context that we are working on. So we have a bunch of points that we're going to take as vertices of some hypergraphic data, and we assume that the connectivity structure of some discrete space is given by, as I say, some graphic data. In this case, let's just assume it's an undirected graph. So we can talk about paths, and we can talk about tangent bundles and all the kind of things that were already discussed in the last live stream, and tangent spaces and vector fields and so on. Now, when we got to the definition, so it's obvious so let me just emphasize the dependence on the definition of a vector field with the graphic data that you have. It's almost obvious that by saying that I have this graphic data and that this is my tangent bundle, which is basically the sort of directed paths, the directed graph induced by the undirected graph, it's obvious that your definition of vector fields is sensitive to the graphic data of your graph. I mean, this is kind of by construction. There's no mysterious there. But in terms of when you try to define functions and you just say, okay, this, I'm going to map my vertices to Z or to some field, then you're immediately forgetting about the graphic structure, right? Those objects do not know anything about the graphic structure. So the motivation, so this is the general question, right? How do we make the graphic structure relevant to the functions that need to be evaluated, right? So that's one first question that we encountered. I mean, I was thinking about this for some time, and Uti and I had some ideas, but it became abundantly clear last week when we ended up mentioning this edges as places idea that we couldn't escape this, and it was good. It was a good thing that we couldn't escape it because it showed many sort of possible solutions to things that were unclear before. So, I mean, just to illustrate what a possibility of the resolution of such question could look like, imagine that you have this kind of situation in your graph. So you have x, y, z, three vertices, and you have some edges between them, right? Now think that x, y, z are the values of some function on those vertices, right? So it's obvious that if you take whatever values x, y, z, you can say that the change of values between the maybe can I actually So if I call this 1 and I call this 3, I call this 2, right? Just the labels for the vertices. It's clear that you can say from x to y, from 1 to 2, there's a y minus x difference. From 2 to 3, there's a z minus y difference, and that matches with from going from from 1 to 3 with that sums up to a z minus x difference, and that works out. Now the problem is that for any x, y, and z, that's true, right? So there's no way to know that there was in fact a path between x 1, 2, and 3 in this particular topology, right? So one way to address this or to come up with a possibility is to essentially assign values to the edges that are between the vertices, right? So if you think, I've said this many times in the past, and some people in the audience might know me from always trying to think of vertices as one edges and sort of trying to have this parsimonious view of edges. So if you now think of vertices as one edges, then you say, well, I mean, a function is assigning values to one edges, so why not to two edges as well? And why not you keep on going, if you have higher edges? But for now, let's just keep it at two edges. And you say, okay, so my function gives x, y, z in this way, but also gives a, b, c to the undirected edges between them, right? And so you can say something as trivial as, for example, that c is the average between y and x, right? It must be y plus x plus y over 2 or something, right? Or you just assume that c is the change from x to y, right? So you assume there's maybe a proportionality between x and y. Some conditions, right? There are some conditions that we can come up with that will constrain, given a set of values, will assign to x to 1, 2, 3 and the edges between them, will actually constrain what are functions on those elements, right? Just by the topology of the graph, right? And so, if you want to assign x, y, z independently, you can. But if you want to assign x, y, z and a, b, c, you can do it independently, right? There are some constraints already on how to impose. So that's sort of the more primitive example of what a function could look like in this context. And if you think about it, to me, intuitively, before we go into more details of these edges as places and what it could mean more generally, which Nick had very nice ideas about that. But to me, intuitively, it's obvious that if we're going to have a notion of like a native notion of continuity, discrete continuity, whatever that means, right? It's clear that we have to involve the edges in some essential way, because the edges is what define what continuity means, right? In some sense, it's what defines connectivity. Therefore, it's going to define what continuity means. So I think something like this is going to be necessary some way or the other. I have been thinking about the different possibilities, the proportionality one, the average one. I'm not particularly liking the look of any of these, because they seem a bit artificial, to say some arithmetical average here or geometric average there. I mean, it doesn't ring very natural to me yet, but it's clear that something like this has a lot more potential to in a finitary discrete way that is sensitive to the graphic data. That's something that allows you to define continuous functions or smooth functions or something like that. And I suspect, by the way, that the notion of smoothness and continuity is going to be one and the same. There won't be a lot of freedom to choose what is the analog of smooth, what is the analog of continuous, or what is the analog of C5, C27, C300. I think those are all essentially going to collapse, like many other notions that we've seen so far, that in the discrete case actually collapse and become much more constrained. So anyway, so that's the first motivation, to think of edges, and so the idea of edges as places came from two different directions. It was kind of an interesting back and forth between Nick and I, because Nick was saying, so why don't we think of edges essentially taking a dual perspective, and why don't we think of edges as the points of your space, and we think of the vertices as the overlaps. So sorry, the edges should be the points with the neighborhoods, so the neighborhoods of your space, and you think of the vertices as the overlaps of those neighborhoods, which I thought was a very interesting perspective as well, and one that I think is clearly intuitively reasonable to consider. And then on the other hand, I was thinking, okay, so if I want to still have a clear notion of path in a geometric context, so that we can do all this sort of algebra stuff and vector fields and curves and so on, I still need to know what the points of the manifold are. And to me, it made sense that if we give the data that is essentially, sorry, how do I think I have to select like this and just delete, I believe. Yeah, maybe not. Yeah, whatever. So if I have a graph that looks like that only has 1 to 2 and 2 to 3 edges, it's obvious to me that this graph is fundamentally different from having the full triangle. And so if a space has 1, 2 and the edge 1, 2, the vertices 1, 2 and the edge 1, 2, that's telling you that there's a place in 1, there's a place in 2, and there's a place between 1 and 2, right? And that is whose in-betweenness is exactly 1 and 2, right? Similarly with 3 and 2. Yeah, go on.
Can I interject at this point? So
please.
When like right at the beginning, when we first started discussing this program, when we were kind of brainstorming, you and I, Carlos, possible translations of things like open sets and so on to the discrete context, we kind of floated this idea that's come up in a few different contexts of saying, well, if you allow for essentially for kind of dangling, in the arity 2 case, if you allow for sort of dangling edges that don't have a vertex at one end, then that gives you a kind of very nice notion of how a limit point might work, right? That you've in a sense it's like you have functions that are evaluatable at the vertices, but then there are also values at the edges, even the edges that are dangling that don't have a vertex at the end, and those are the analog of your limit points.
Sure.
And so I'm wondering if what's happening here, either in this perspective or possibly in Nick's dual perspective, one or the other, is we're essentially reconstructing something of that flavor, right? That where what you are doing when you evaluate the function on an edge is that you're effectively taking you're evaluating the function not at a point but at a limit point.
Right. That I think is probably within range of the descriptive power of this framework, I imagine. I don't know, because so the idea is that so again, I have maybe it's a prejudice, but I have a tendency to think that the n edges are all equal in some sense, and so one edge data looks very distinct to us because of how we've studied graph theory historically, but it's, by looking at these things, and doing all the rewriting that we've done with the hypergraph backlit and struggling with all these kinds of things, to me it seems that we should really think of edges, as graphic data that lives on some kind of memory slots that are the actual mathematical vertices, the kind of things that are floating that can be sort of highlighted by some edge structure on top of them, right? And to me, then that means that if it at some point makes sense to think of functions on vertices and vector fields, which are edges in some sense, and curves and so on, then I think it makes sense to just assign function so numerical values to all edges and to have it be more parsimonious. Now, in terms of what you're saying, I would say exactly yes. I mean, I would say that's what this allows you to do that previously it's impossible, right? Because previously the only way that you can relate 1 to 2 in terms of a functional value is because they are numbers, and so it means that they are not any more special than 1 and 3 or 1 and 7 or 29 and 300. Who knows? It's just numbers, right? There's nothing intrinsically there's nothing in the information that you're provided that allow you to do that. So I mean, this was a suggestion so that we can start to think about this direction, because some things clearly change if you think of edges as places, and to me, the fact that you can have a triangle in the middle here. I mean, I don't know if this is going to be sensible to do freehand, but yeah, if you have a triangle here in the middle, some kind of undirected edge. In my opinion, this is an interesting example of why this makes sense conceptually. I mean, this is telling you that in this particular space of 3 points, right, you have, or well, 3 points of 3 vertices, you have, a place that is connected to another place by a sort of a binary path, and then to 2 other places by a ternary path, right? So 1 is connected to 2, but it's not connected to 3. And it's only connected to 3 by saying that there is space in between 1, 2, and 3, but there's no space in between 1 and 3, right? So in some sense, it's like when I look at a hypergraph, in all its glory, in all its order, by telling me sort of discrete geometric information, what I'm saying is this sort of betweenness data, essentially, right? It's like you have like some first selection of locations, your 1 edges, and then all the other information, or your vertices if you want, and then all your other information is betweenness data for those, which imply existence of other points in a way, right?
Okay, hang on, hold for 1 second. Sorry, because this is an interesting structure which I don't think, which probably is second nature to you, but I don't think I've ever thought about. So forgive me for
No, please,
slowly.
yeah, this is the point, yeah.
So it seems like what you're proposing here is, so okay, suppose we have a transitively, we take an arity 2 transitively reduced graph.
Mm-hmm.
There is, I guess, an inevitable consequence of what you're saying is that there is a canonical hypergraph that you can produce from that by taking all length 2 paths and producing a 3 edge there, and all length 3 paths and producing a 4 edge there, and so on.
Yeah.
And so somehow, so every directed or undirected, 2 graph, whatever you want to call it, induces a canonical hypergraph whose maximum arity is the maximum path length.
Correct.
Right.
Yes. So
yes. Do we have a name for that? That seems like that should have a name.
That should probably have a name. My thought is that that's one way to define such a space, right? You can just start, as you say, with the graphic data, and then you start to do sort of transitive reduction and or basically considering paths, and those define betweenness properties of your points, and effectively you can capture those in edges. Arguably, your edges would probably also want to be oriented somehow, because you might want to keep path sequencing, but yeah, I mean, that's one way of defining such graphs, and obviously
it's a sort of hypergraphical transitive closure, right? You're
yes.
You're transitively closing, but instead of adding new edges, you're adding hyper edges whose arity
Yeah.
is 1 greater than the path.
Yeah. So the one thing I would say though, and this is delicate, and I think this is a very important distinction. And so thanks for that question, because this highlights a very important point, which came up later when we were thinking about what vector fields are and how to define the infra-calculus of vector fields, or infra-vector calculus, or whatever, something like that. So the point that you're making is, if you give me graphic data, you just said you just have conventional graph, right? But any graphic data, any hypergraphic data, it's clear that if you take those as your places, let's just call them places for some neutral word that is it could mean flexible things. Then for me, places are the things that I'm going to traverse and I'm going to travel through or travel to somehow, right? So a sequence of places, it's a journey, and or in mathematical terms, a sequence of points is a curve, right, or a path in this context. So it's not an arbitrary sequence of vertices or elements. It's a sequence of elements that are connected. So it's a viable sequence of places in this context. So it's going to be a sequence of edges in general, and it's going to tell me how I navigate the space. And so to make the distinction here, can I maybe change the color here? Oh yeah. So imagine what happens when I go from 1 to 3, right? And I go the long way, right? The long way here means I go from 1 to where I call here C, and then from C to where I call here 2, and then stop here, then to B, stop here, then to 3. Okay, fine. That's the green path that went from 1 to 3. But then if this is the space that I have that has a 3 edge in between them, I can also take this more direct path, which is 1, then here, and then directly to 3, right? So these are effectively 2 different paths, right? In reality, if you have 3 cities or something, and you know that there is in between space, there's not a vacuum or not an ocean or something separating them in the middle, that you can actually travel in this shorter way, right? And so this sort of triangular inequality sort of situation that just grows naturally out of the hypergraphic structure, I think is quite flexible. I think it's quite amenable to the path treatment. And so to your question, these paths here, obviously they do define some kind of hypergraph, right? Like you count these things and they become a hyper edge for some hyperstructure. What I would say is that is what I would like to call something like a path hypergraph, or some kind of just like people call the path group poly or whatever of a smooth space or whatever. Those could be the path hypergraphs or the path graphs that you have on top. And it might well be that we need to, given a space, a discrete space, which for me is sort of like a God-given hypergraph, an honest, undirected, God-given hypergraph that is just like set in stone. It's static, whatever. That's your hypergraph. Static until you rewrite it, but for a time, just static. And then on that, you have all this path structure that, each edge is a place, in this parsimonious sense. And then you can have paths be this generalized sense of path, which is not the naive, sequence of vertices that contain some edge, which is what a lot of people do, certainly in graph theory. But this slightly more generalized notion of path, which is it's a viable sequence of edges, right? Which is our placeholder for places in this more general sense. So anyway, I think that was so that's kind of in a nutshell this motivation for edges as places. And again, the main thing being that we need some kind of handle for functions to be sensitive to the graphic structure. So having something that needs to happen in between, right, seems probably reasonable. And the other thing, the other thing is that when you get into the rewriting sort of approach, it becomes quite clear that you need to think of hypergraphs of paths as something that sort of, it's a bit like the tangent bundle, right? Like, I mean, I think it's a very good analogy from the usual geometry picture, right? So in geometry, your initial space, your manifold, is some God-given set with a connectivity structure, smooth, continuous, whatever. And then, you perform some constructions on it by saying, oh, I have curves, embeddings of, intervals and things like that. And then you end up constructing this tangent bundle that, sure, now it's another smooth manifold. You have some nice diagrams and all that stuff. But, at the end of the day, what you did is you started from a manifold and you built a new manifold, which is not the same manifold, right? And it's not a sub-manifold or anything like that. So I think this is very similar to what I'm proposing here, that, you're given a hypergraph, that's sort of the honest locus data, that's the places of places, like that's just given, static. And then by doing some interesting constructions, which we still need to figure out the technicalities of, you will build probably a single other hypergraph that is going to be the sort of vector hypergraph or the tangent hypergraph or whatever we call it, or the path hypergraph, whatever name we use, that is going to include this kind of higher, transversal information. And there's, by the way, there's not only going to be a path hypergraph, there's going to be a sort of copath, there's going to be a bipath, sort of like bivectors, and all these kinds of things. All that analogy just runs very smoothly in between the continuous case and the discrete case. But I think there needs to be some kind of placing ourselves on a set hypergraph that is sort of like static and God-given, that cannot really be changed, and then doing constructions on top of it so that you have the same mentality of hypergraph rewriting. And by the way, that's where the hypergraph rewriting for algebraic purposes becomes particularly powerful, because you do hypergraph rewriting for the base space to do this sort of WPP style generation of spaces, and that's more sort of like unstructured and more sort of statistical in nature in a way. And then once you have one static space, one static hypergraph, then you can do all this analysis where you generate its path hypergraph, and that hypergraph can be rewritten, and you have the notion of what a field, vector field or a tensor field is in that hypergraph, and so on. Anyway, that's kind of the brief summary of why we ended up with this notion and what it could be.
Okay, that's super cool. I'm still internalizing a lot of this. So in the edges as places thing, these hyper edges that are induced by this operation, hypergraphical closure, whatever we want to call it, that are unbounded arity, all of them presumably are assigned an element of the field under this function, right?
Well, that's the thing. So that actually that's a nice way to begin to see what the structure is. So what I would say is you have your base space, which is this given hypergraph, static hypergraph, a function in that space, a field for that matter on that space, but let's just keep with functions, is an assignment of number values to edges, right? And I think we should, if we want to be very literally geometric, I think we should keep that hypergraph undirected and unlabeled, right? So it's just, sort of just places, right? It just has information. It just has information about connectivity. So a function is an assignment of that. Now, if you go to this hypergraph that is this sort of transitive closure or path closure kind of construction, then you might start to assign the natural. So the natural quantities assigned to paths are precisely finite differences, right? This is what we had. It's not that we were doing nonsense before. This is important also for viewers to know that it's not that we are now just sort of scraping everything that we did before and it's like say, no, we're going to do something else. What we were doing before was effectively just somehow, sort of ignoring the fact that there's space between the vertices and just doing some kind of like one edge approximation of the full story, right? Which is similar to what we would do if there's actual higher graphic data and we keep at the 2-edge level, right? We would do a 2-edge approximation of the actual story. So the natural construction is finite differences, and so you could assign to any edge that is defined by a sequence of edges, right? One of these whatever finite differences. What I find it's interesting is that so there's something interesting and something difficult, which is usually come hand in hand, right? So something difficult is that you technically now have hypergraphs. We probably don't want to overstate this term too much, but we do have the notion of collections of edges as
right. This is one of my concerns as well. It seems like we have inadvertently just invented symbolic expressions, right?
Yeah. But at the same time, yes. But actually, I would say this is almost to be expected, because if we are in a discrete finite context and we are thinking of the notion of path in a very general sense, then I don't think you can escape the fact that you're essentially going to build words with your your labels, right? I mean, the path is going to be a word with the labels of the elements that you have, the discrete elements that you have in your system. In our case, previously our system was just vertices because we were not in the edges as places kind of mentality. But if you are in the edges as places mentality, then your things are the edges. So edge words are natural notions of paths. And yeah, it's so. I just perhaps more philosophically, but if I look at this diagram here on the screen where the two binary edges and the one ternary edge actually have different information, if you have a function that assigns whatever, there should be something else assigned there, right? Like some a, b, c, I don't know, t, that is assigned to the actual triangle as a real function. It makes sense that if your data, your locus data, what your discrete space is, includes these binary and ternary edges as something as meaningful information, it makes sense that a function should assign some value there, and that in principle, that value should be largely independent from the x, y, z values, to the point where you might want to say something like you need to be within the average or something. I mean, there may be some constraint. But if you do the trip XYZ or the trip XTZ, those two things can be different, right? So if we wanted hypergraphs, not just graphs, but actual hypergraphs to be our placeholders for space, I think this is a natural thing to consider, because otherwise, yeah.
Absolutely. But hang on, but I feel like you brushed a lot under the carpet just now when you said, oh, there might be some constraint or whatever.
Okay, sure. Yeah, I did. I definitely did. Yeah,
it's just like, so because so I think this is lovely. I think this idea of so you just have, okay, we no longer make any distinction between vertices and edges. You just have edges, and then we say, okay, so you have paths that are just sequences of edges, and then we produce a kind of a hyper edge, or whatever we want to call it, that corresponds to each one of those paths, and that produces this hypergraph closure or hypergraphical closure, or what whatever term we settle on. So by default, you are assigning field elements only to the original edges, right? Yeah. That's the definition of your function.
Yeah.
Now you've got this hypergraphical closure. You've got a bunch of these hyper edges that you didn't have before. And it seems to me, okay, so, what would it mean to assign one of those hyper edges to a field element?
I don't have a meaning for that, though. I mean, that would be like so let me rephrase your question in the continuous setting and see what happens, right? So,
well, I was going to say in the continuous setting, the obvious answer is it's an accumulation point, right? That you have a function that's defined over a topological space pointwise.
Sure.
But you can also assign, if you take a sequence of points, you can assign a value of the function. You can assign a generalized value of the function to that sequence by taking the accumulation point of the sequence.
Oh, okay. Wait. Okay, I see.
And then which sequence do you use? In other words, like which path you take can change based on, depending on the topology of the space, can change what accumulation point you end up at, and
sure.
Therefore what the value of the function is.
Sure. I mean, okay, so maybe I had the same picture in mind, but what I was thinking is, if you have a space and you have your groupoid, your path groupoid on that space, right?
Mm-hmm.
I mean, in the smooth case, this is actually a nice, Lie groupoid and whatever. So having a function on that space is having some kind of functional for curves, right? It's giving you this sort of functional for curves, and which I'm not saying it's not interesting or relevant, but what I'm saying is that it's perhaps not the immediate thing that we need to be concerned with if our priority is to make sense of this as a model for geometry, like in the basic sense. Because I mean, if I am trying to reconstruct geometry, the first thing I'm gonna worry about is not whether I can recover functionals over curves on my base space, but whether I can recover something like an algebra of curves or an algebra of infinitesimal curves and these kinds of things, right? I'm not dismissing it. I'm just saying that that and also that this hypergraph, it's kind of a virtual hypergraph. It's sort of this sort of emerging hypergraph, and as such, you much like in the Lie groupoid case, the path groupoid case. I mean, the actual space of paths, right? This is a set, right, where you have all paths, and you have concatenation as a partially defined operation, right? That thing is a groupoid, right? But it's an infinite, nasty, big groupoid. It's not good, right? But once you take homotopy equivalence and you do things nicely, then you actually can reduce to the path groupoid of the space, into your pi one, capital pi one of your space, and that's a manifold, right? Like that's a finite dimensional manifold whose Lie algebroid is the tangent bundle of your manifold, right? So it's a nice compact story, like you have a tangent bundle, which is a finite dimensional Lie algebroid. Has its integrating Lie groupoid is the path groupoid of your original space, right? So everything stays within the finite dimensional manifold category, right? No problem. So my view is that what we are thinking of when you mention like these sequences of edges as generalized paths in this context is going to generate this path groupoid, right? Not the the general groupoid, the partially defined composition path set, right, before taking any relations. And I don't know if that's the right space to look at, right? Like we might need to say things like shortest path kind of thing, and do some kind of quotienting effectively of that hypergraph so that it becomes something that is more useful and more manageable, and effectively that becomes something that is of the same nature as the original hypergraph. Just in this case where you define something that is a partially defined groupoid, so a partially defined composition of paths in a very infinite dimensional space, but you do something interesting and clever and that is compatible with your local structure, and then you end up with an actual honest finite dimensional manifold, right? I think the analog here would be, we potentially have this very odd hypergraph that we are thinking of, as sequences of hypergraph kind of thing, and it's not very nice. But there might be natural constructions there that basically tell us, sure, it's a bigger hypergraph, it's not your original hypergraph, it's a bit more complicated to interpret, but it is still a finite hypergraph. And because paths don't necessarily have finite length, right? I mean, they don't have bounded length. That's what I want to say, right? You can, in principle, have arbitrary length paths, right? So your hypergraph, in principle, is not well defined because you don't know when to stop, right? So yeah. Anyway, so these are the kinds of things that you might want to consider further down the line. But first, I think what we should probably discuss in this meeting, if you...
Sorry, I'm getting a bit lost.
Yeah.
Can Jonathan, can you explain why did you say it was an accumulation point?
So, okay, my intuition for this is as follows. I'm going to make a couple of there are important caveats here, right? But so okay, so you start from the base hypergraph, as I think Carlos is calling it, right? This God-given hypergraph, where we just have hyperedges and we don't make any distinction between them. Then we evaluate paths and we construct this hypergraph where each hyperedge in that is effectively a sequence of edges in the original. Okay, so now I'm still sort of working on this question. I was trying to think about this question of what would it mean to assign those hyper edges to field elements. And okay, so as Carlos correctly says, that is effectively a functional acting on paths, right? Mm-hmm. Or if you like, a function defined on the path groupoid.
Yeah.
So okay, just thinking about what examples of such things do we know? Well, the limit of the limit of filters, that construction in topology is a function on it's a functional on filters, which are themselves collections of points, right? And so okay, in this particular case, I think, I mean, there may be some clever way of defining it so that this works, but I don't think paths quite satisfy the axioms of a filter. I don't think you have upwards closure. But there might be something similar to the category of filters on which we can then define a functional, just like we do when evaluating limits of filters in topology. And so but that construction, of course, then gives you the notion of or a generalization of the notion of an accumulation point of a sequence. And so it allows you to assign a function value to a sequence of points or a path of points rather than just a single point.
Sorry, what is an accumulation point? Is a limit point. Like, what is an accumulation
Yeah,
point?
exactly. A limit point of a sequence.
Okay.
So suppose you if you have a sequence, yeah, you can just take the limit of that sequence. More generally, if you have a filter, you can take the limit of that filter. Or if you have a net, you can take the limit of that net or something.
Okay, so you're saying that I define a function on each of those edges. And so if the function is continuous, then I have the value at the limit as well. Is that what you're saying?
Well, okay, so what I'm wondering is, can we build towards a sensible definition of continuity in that kind of framework, right? So what Carlos was saying was, like there are probably some natural constraints that are going to exist on what function values you can assign to these hyper edges based on the function values that have already been pre-assigned to the elements in the corresponding paths. And we can argue a bit about what those constraints might be. But they probably have, as Carlos says, they probably have something to do with finite differences, averages, something. But suppose we know what those constraints are, then then whether your function, whether your assignment of values fits those constraints, to those hyper edges fits those constraints or not, determines, if you like, whether the function is continuous.
Right. That's cool. But in that setting, we're not looking like our embedding of the graph isn't exactly like correct as it should be, because Carlos first said that the triangle, like the hyperedges that we form by taking the transitive closure of these paths, if I assign a field element to those, then it just looks like that it should be in between or something like that. But if I treat them to be like accumulation points, then the visual picture is like very different. Like it's wrong, right? Like it's like earlier we were thinking even in the smooth case.
That's why maybe I shouldn't say accumulation. That's why maybe we should think of it more as like something more abstract, like the limit of a filter or something, right?
Right.
But the point is, okay. Let me now make the sort of the quasi-philosophical remark. So the point you were making, Uti, is of course completely correct, right? That if you just have a finite collection of points, you can define, then you can define a continuous function between the, that sort of interpolates between those points, and it doesn't matter how large that set becomes, you'll always be able to do that. So in a sense, what we want, okay, here's at least how I'm thinking about it. When you do this operation, this hypergraphical closure, one way to think about what you're doing is you assign those hyper edges to elements of the field. One way to conceptualize what you're doing, maybe, is that you are saying in what way you intend to take the limit as that graph goes to infinity. Right? And so the point is that there are ways of taking that limit in which the function you've defined is continuous, and there are ways in which you've taken the limit in which it's not. And so the argument would be each of those different ways corresponds to a different assignment of field elements to those induced hyper edges. And some of those will be compatible with the conditions we agree upon, and some of them won't. And the ones that aren't will be the ones where where that function has not limited to a smooth function.
Right. So basically, you're saying that in the limit, these hyper edges should correspond to concrete geometrical things that we can see.
I think so, because I guess the point here's again, this is a very hand-wavy sort of intuition, right? But the point you might make is, okay, what happens when you take the infinite limit of a graph? Well, you lose some ability to resolve the individual points, right? And so at some level, all you can really resolve are paths and things constructed out of paths. And so one of the key conditions from a conceptual level that needs to be satisfied if you're going to have a well-defined limit is that somehow the values of the function, over the values of functions over those paths have to be compatible in some strong sense with the values of the functions evaluated at the individual points. And if that doesn't happen, that's kind of that's the case where your infinite limit has failed. And so when you do this hypergraphical closure, what you're doing is you're saying, this is the value of the function I intend to assign to this sequence of points. And then you can ask, is that compatible with the values of the functions at those points?
Can you explain this in like a one-dimensional case? Like, let's say you're growing out a graph to infinity and you get like the real numbers. So what
Sure.
would the hyperedges correspond to in that case? Like,
okay, so your underlying graph, you have a bunch of edges. Those edges are real numbers, or possibly two edges between real numbers.
right.
Then you construct this hyper graph, and that's going to contain all possible real numbers. Whatever subset of the reals you started from, that's going to contain all possible real number sequences of those, of that subset, right? And so then, if you can assign, so then each one of those sequences will have a limit point. It will have an accumulation point, right? And that accumulation point has to satisfy certain compatibility conditions with the elements of the sequence. It can't be completely you can't just you can't take the sequence 1, 2, 3 and arbitrarily assign it 72 as its limit point, right? So there has to be some compatibility between the limit point you assign, the limit value you assign, and the elements of the sequence. And so then, if you can do that consistently, then that assignment corresponds to a well-defined limiting operation. And if you don't, then it doesn't. Would be.
I'm still trying to wrap my head around this, but it makes sense. It makes a little sense to me.
I don't. I'm not claiming this is a solution. I'm wondering whether that. I'm wondering whether that makes sense as an interpretation of the assignment of field values to these hyper edges, or whatever we're going to call them.
So it might be clarifying to actually spend some time pondering on the specific conditions that we want to impose at the base level, because
yes,
that's actually unclear to me. I've been thinking about this for a week now, but it's actually not very clear. I mean, not only about this, obviously, but it's not obvious, because I mean, you begin with this intuition that vertices is what matter, right? And you're traveling between vertices, and that's your main sort of landmarks, so to speak, of your space. And then you want to say something like, all right, so what happens between 1 and 2 is the average of 1 and 2, or something like that, right? But maybe you want to be a little bit more sophisticated, and if you want to end up with something that looks like a topology, you probably want to demand that your numbers have an order, at least, right? Or at least something like an absolute value or the like. So you can say something like, if your value at 1 is whatever, x, your value at 2 is y, maybe you want to say something like, c is between x and y in this order. Like, I mean, I'm not quite sure that we want an order as strongly, but something like that. I mean, because otherwise, if it's only numbers, if it's really only a field, and you're not assuming anything beyond just a field, then the only thing you can do is to impose some kind of arithmetical condition between these values, right? And it would be quite easy to say, well, what can you do with these things, right? I mean, not much. And you can add them together. It's either geometric average or arithmetic average, right? There's not much more room for operations. Now the question is, why choose one, or why one or the other, right? What is the purpose of this? And that's where I think it gets tricky, because in a way, as Nick mentioned last week, this perspective is basically taking the line hypergraph and make it, take all the line hypergraphs, all the line graphs of all the hypergraphs, right, that you have, and then you effectively do like honest paths on those, right, where you forget the lines are coming from distinguished vertices, and you just do paths on those. So it becomes unclear if you actually do that, it becomes unclear that you should be imposing conditions on some vertices and not others, or what is to say, imposing conditions where the values on edges are constrained by the values on vertices. It feels to me that the constraints should be quite symmetrical in some sense. It should be, it shouldn't be something like, yeah, the value c must be x plus y over 2 or something, because it seems very childish to do that. I don't know. I mean, I don't know what you guys' intuitions are about this base hypergraph conditions on what is discrete continuity. I mean, it's kind of a contradiction in terms, but
right. I mean, maybe this is a completely spurious intuition, but something in my brain is screaming sort of renormalization group flow, right? Because in a sense, you're starting from a function that's defined purely at a vertex level, maybe, let's say. And then even before we take the hypergraphical closure, then we also have to, because we are not making any moral distinction between vertices and any other hyperedge, we then have, function values assigned to the hyperedges, and those presumably have to be compatible with the vertex values in some way. And then we take this hypergraphical closure, and the values assigned to those hyperedges have to be compatible with the elements of those sequences. And that feels very similar to when you define like block variables under in renormalization group flow. Those have to be compatible with the kind of with the underlying variables in some symmetric way. Except I think I don't know that much about RG flow, but I think it's not symmetric in certain cases, but it is in many. I don't know, it feels very much like any of these cases where you have compatibility conditions between kind of micro scale variables that you're coarse graining and their coarse grained analogs. But maybe that's, as I say, maybe that's a completely spurious.
No, that might actually apply to the case of, say, like the past hypergraphs that we were describing before. But I still think that the problem is very sort of single level in a way that there's no coarse graining yet when you're just looking at a hypergraph. This one hypergraph that I have on the screen, right, like 1, 2, 3 with 1, 2, 2, 3, and then the 1, 2, 3 edge, right? This particular one. What are the valid functions on this? Say valued on z, right, on the integers. Like there should be it should be an answer that is very obvious, right? Like I don't think there should be a lot of philosophy of what could be continuous. I mean, and I am not seeing what that obvious answer should be here, right? Like,
but I mean, is it not a reasonable intuition to say that the value at C should be you could consider that like a sort of block variable constructed out of the values at 1 and 2, or values x and y?
Maybe. I mean, I guess my background intuition is, because I'm thinking of edges as places, I want to eventually recover the notion that I'm traveling through these and I'm recovering something like a directional derivative or things like that, right?
Right.
So, or what you alluded to earlier, which I think was a path continuity, right? That could be an unrelated. It is possible that an unrelated notion in this context is path continuity. You might have like sort of continuity, I don't know, spatial or connected continuity or something like betweenness continuity, maybe is a better name. And then you might have a path continuity, right? Which is some condition, as you said, on the paths themselves and how to how the but the betweenness continuity to me seems like yeah,
this is like very, I mean, this is gonna sound extremely like basic, and probably everyone has thought of this, but like this just sounds like to me that taking like these closures is saying that, hey, there is a place between like the sequence of edges formed. So essentially, if let's say xy is an edge and y z is an edge, then xy plus yz is also like a place. So that basically means that that boundary xy plus yz is coming from another place, which is essentially saying that the homology groups are trivial, like we filled in the holes essentially.
Yeah.
That is what I'm thinking. So if I
so
dig
what is the condition then? What is the condition?
Sorry?
What is the condition that you draw from that? Like, how do you constrain the value, like t, what I call t, which is the value that you're assigning to the triangle if you know x, y, z?
I don't know. I mean, I don't know if simplicial geometry, like when you triangulate a surface, like I don't know whether there exists some theory of functions on a simplicial complex or something.
Well, the problem with simplicial, yeah, go on, Jonathan.
Well, there's Morse theory, which is pretty much that.
Yeah.
yeah, I mean, there are constraints that you can derive for analytic functions defined over the, you have an analytic function defined over a topological space, and that places constraints on the analytic functions you can define over its CW complex and vice versa. But those depend in sensitive ways upon details of the gluing maps and things for the for the cells in the complex, which I guess in our case is basically equivalent to saying our constraints will depend sensitively on the graph topology.
Which is what we're saying, exactly.
Right.
Yeah.
So I agree. It's an analogous problem, but I'm not convinced it directly helps us.
No, I don't think it does. I mean, because as you just said, it's basically it is done there in that context in sort of a reverse of sort of a triangulation, right? Like a triangulation of your surface, and you have all the gluing data, and then you can somehow encode that into this complex and this discrete functions and so on. But here is different. Here is we already have the discrete information, right? We have the betweenness information or the adjacency information, and then the question is, what is the right definition of a continuous function in this context, so that we recover the notions that we want. Perhaps it might be better to look at the next step, is like, what do we want to do with these things, so that we recover what we want.
I guess for discrete cases, you can get like any condition that you want, but like the condition will be constrained by what we want to get in the end. So we should.
Yeah, exactly. I mean, I guess that's the question, which I think is not obvious, right? Which is there a way to answer this without somehow making an ansatz for what the thing, what space we are expecting the thing to limit, the graph to limit to?
Right.
If you make that ansatz, then I agree. Then it is basically like Morse theory, right? Then it is just like, you know what analytic function you want to achieve in the limit, and then there's fairly well-defined theorems that tell you what constraints that places on functions you can define over a simplicial decomposition of it. What we're trying to do is somehow, we're trying to ask the same question, but without having to make a guess of what the thing's going to limit to. And maybe that's just impossible. I don't know, but
yeah, I mean, I was just thinking that if you have, I mean, to me the problem is, the way I'm formulating the problem to myself is something has given me this finite hypergraph, right? And this something might be one of the algorithms that WPP or whatever. I've been given this hypergraph, and now I want to do geometry with this data. I'm not going to take limits. I'm not going to, this is the exercise I've been working on, so to speak, right? In my research process in these last few days. Like, I'm giving a hypergraph. I'm not allowed to say anything about infinities or do limits or anything like that. But I just want to do geometry on this with this literal data, right? With this finite explicit data. And so for me, one of the goals would be that, exactly what we did with finite difference operators, right? That you can identify a structure that effectively allows you to do dynamics in this algebraic sense, right? So you can think of all the possible dynamics of your space, and you can think of the sort of the kinematics of the possible movements in your space, and that has a natural algebraic structure and so on. So in this particular case, where the paths are in a way, defining this higher or this hypergraph or something, right? It might be that all the actual active hypergraph rewriting theory that we talked about last week happens on that hypergraph, which, I mean, we call it hypergraph, but once it's defined, it's just another hypergraph, right? It's nothing special. And yeah, so it is very open-ended to me at this point, because previously we did have this reference of like, oh, if we find something like a Lie algebra or the weighted analog of a Lie algebra and so on, it seems that we had like a tail to chase, so to speak. In this context, I think we sort of lose the trail, and then we start to actually wander around in the jungle, and there's no clear direction where to go. Because I think that the other question is the other part of the live stream that I wanted to do today is to do with rewriting rules, and this is something I mentioned during Stephen's live stream, where I think some of the questions that we were tackling last time about addition of vectors and composition of vectors and things like that, I think have a very nice story, have a very nice sort of like summary if you take it the perspective of rewriting. And I don't know exactly how that matches with this. I mean, it's kind of orthogonal. It doesn't affect this debate in some sense, but it might also offer some additional information on what to think of this hypergraph that emerges from paths, right? So I don't know if we want to. I mean, I haven't heard from Nick. I'm curious to see if Nick has some intuition about. So, like, if you were to, like, your life depended on this, like, what would you define as a continuous function in this setting, like with this kind of discrete data?
I think last time we had this idea of if you do this similar closure operation, like taking the line graph or graph, define the continuous function is that this operation would produce the same graph, or at least a subgraph of it. So basically, whatever operation of your closure is of assigning values to these hyperedges, continuing this operation again and again should produce the kind of the same substructure that you started with.
Mm-hmm. Okay.
Right. So it's kind of contained in whatever higher before structure, so that you can build this tower of this closure. It would make sense kind of to me, at least that.
So can you explain how that would work in this particular example of x, y, z, like 1, 2, 3 with two binaries?
Well, I can explain by on Uti's favorite example by just taking the path graph of numbers. If you continue this line graph operation, basically get the line graph again, obviously, right? So that's kind of reminds you that it's already some discrete version of the continuous thing. Whatever values you assign, if you already have values on the vertices and you are like assigning some kind of averages, maybe this operation would even produce the same values. But even without assigning any values, just by structure alone, if you get the same kind of subgraph of the previous graph before you're doing the closure, this operation may basically define the continuous operation, or the continuous version of a graph with some default values on it. I don't know.
But that's kind of identifying a family of graphs, right? Family of hypergraphs.
Yeah. But if you have some values, you can also constrain on the values too, so that they also have the same values before you do the closure.
But how do you transform the values when you do the closure? Like how...
Well, that's what we're trying to do. If you assign some value, like taking the average, right? If you take the path, you do the closure with the hyperedge, you basically make some kind of average of all the values that you travel around, or some limit, or just some whatever. After you do this closure, you postulate that you have to find the same subgraph with the same value on the graph that you started with.
Yeah.
Right.
I think you're saying, I mean, if I understand correctly, I think you're saying something that is entirely equivalent to what we are saying here, but I think the question is, what is the actual operation on the values that you want to match, right? Because you will have to check that whatever closure does to your edges and your values matches to whatever values were on your original hypergraph, right?
Well, maybe the value that you have to find it. You can do it symbolically. Like you can assign a symbolic value to each new derived hyperedge, and then you just derive a set of equations so that those new value is equivalent to the previous one, and so on. And that basically your operation would depend on the structure itself.
Carlos.
Yeah.
Do you mind if I push back slightly on a comment you made earlier, which I wonder if it was unnecessarily restrictive?
Go ahead.
Which is so the thing you said about you think that there won't be distinctions between differentiability, smoothness, continuity, etc. That in some sense, like you expect infrageometry to work like complex analysis, right? If you can, that there's, analyticity, holomorphicity, differentiability are all kind of the same condition. But let's imagine for a moment that that's not true. And that, so we take Uti's point from earlier kind of to heart properly, and we say, okay, well, give it, if we're just, as you were saying, if we're just operating on the finite data that we have, we're not taking any limits. Well, of course, we know that whatever assignment we make, there's always some limit that's consistent with that assignment and consistent with the function being smooth. So maybe instead of having a kind of binary criterion of is this function on the hypergraph smooth or is it not, we have some kind of way of quantifying how difficult is it to make it smooth in the limit. In other words, you could almost imagine a kind of measure theoretic criterion of how many possible limits are there, or what is the measure in the space of possible limits of ones in which this function is smooth. And that, I suspect, probably can be calculated quite easily using finite differences, right? Because if you say, okay, so if we take this example here, like, you've got 1, 2, 3, and we want to assign a value to t. So if the value t lies strictly in that interval, lies between 1 and 3, then it's like, that's that's the closest we can get to it being smooth. That's the most smooth we can get. If it lies outside of that interval, but within, say, the epsilon of the finite difference, so in this case, the gradient is 1, right? So if it lies within a distance 1 of 1 or 3, then that's kind of the next case, and so on. And so you can essentially assign a sort of discrete differentiability class based on the assignments of the t values. So you could, in principle, assign a t value of 1,000 there, but the point is that you need to have that you're dramatically restricting the set of possible limits that you can take, because you would need to go to extremely high derivatives in order to make that work. And so your continuity parameter or whatever is a lot lower.
Yeah. No,
for some reason.
Go ahead.
Sorry, go ahead.
No, go ahead, Vinny.
For some reason, what I'm thinking of taking this triangle limit as like, and okay, so if I basically say that there exists a t value, which means that there exists a place in between. For some reason, I'm thinking of this thing approaching like a circle, where there's a thing in the middle. So I don't know, like, okay, so if you have like this closed path thing, you can probably add points in between, and you can get something finer. But this t value, which is in the middle, it's for me, it's like it's kind of far away from those edges. So it's like if given a function on a circle, I can extend that to a function on a disk. So the restriction on the t value, like, I don't know if the visual interpretation is correct or not, because if the t value is in the middle, then there's no restriction. Like, how are we visualizing the t value here?
So in what let me slightly correct what I just said, but I would visualize, okay, in the intuition I was just describing, I would be visualizing it as so if these are directed paths, right? So if 1, 2, 3 is an ordered, if that's an actual sequence, okay, then I would visualize the t value as being the limit point of that sequence. Okay. And so what you could do is you could say, okay, so if the finite difference is 1 between 2 and 3 and between 1 and 2. So if 3 is the end point and we want to assign the limit point t, if it lies within distance 1 of 3, then that's kind of that's maximum smoothness or something. If it lies within distance 2 of 3, that's maximum smoothness minus 1 or something, and so on. And so your constraints on possible t values are based on the finite differences of the elements in that sequence and the endpoint of the sequence.
Okay, fair enough. Like for me,
because you're effectively quantifying to what order of finite difference operator would you need to go in order for this to be an analytic function, in order for this to be the limit of an analytic function.
Right. Okay.
Which is the analog, I think, of a differentiability class.
Right. Right. I mean, I still don't get the visual interpretation of t being a accumulation point based on the filter point you said. But it seems like
so if you imagine the even in the continuous case, right? You what does it mean when you take the limit of a sequence, right? You've got a functional that's acting on sequences of reals, effectively on subsets of the reals, and assigning them to real numbered values, which are the limit points. So in this case, you've got a functional that's acting on a sequence of places, in this case 1, 2, 3, and assigning them to a value.
Right, I get that. I get like the algebraic viewpoint.
Okay.
But like I'm talking about the visual point where T is in the middle, like there's a place in the middle. That's
But
the thing.
why is it in the middle? I'm arguing it should be at the end, but maybe that's maybe that's the difference.
I mean, isn't T the value we're assigning to like the place that's bounded by these edges? Like what are we assigning T to?
So that was, I think, the intuition. What I'm proposing is that we should think of T as being the value that we're assigning to the limit of that sequence.
Oh, so you're defining it that way. Okay.
So you take the sequence 1, 2, 3, and you ask what does it limit to, and that is the value of T.
Right. So it's like some additional metadata that you're assigning.
But wouldn't that essentially make the values dependent on paths?
Yes.
But that's undesirable, right? For the base hypergraph, right? Like
for the base hypergraph, yes. I see. So you want to have a notion of continuity that exists even at the level of the base hypergraph before you even do the path closure.
Yeah, well, exactly. Yeah. So there might be a notion of path continuity, as I say, where
sure. Sorry. I was still harping on path continuity.
Yeah. Okay. Just to clarify.
If we're just operating on the base hypergraph, I don't even really know how to think about that in an effective way.
Yeah, exactly. That's a good summary. Because I mean, I like the possibility of taking limits as a as a guideline on how to impose constraints, but I think that at the end of the day, what was happening is that we did have some nice correspondence. I mean, let me just infuse a little bit of hope in the debate, because I mean this is very far from my intuitions and like this discrete mathematics, and then everything is just algebra, and we're very far from geometry. So the fact that we built this the original idea of infrageometry and building these discrete models and using hypergraphs and so on, I think it was obvious to us that there was a very clear analogy between many aspects of differential geometry and all these discrete hypergraphic structures. I think that what I'm still sort of clear or undecided on is when I think from the beginning we've said, okay, let's consider a graphic data, as in 2 graph data, as our manifold. And then many things have followed nicely, right? Like we've had like this vector fields, analogs, and all this, even tangent bundles and connections possibly, and all those things. Which, by the way, the fact that connections might be sort of weighted and might have different values for each of the edges really sort of resonates with the idea that you should be thinking of the edges independently as places, right? Like you go, going from X to Y and going from Y to X might not be the same thing, right? Because that's where your space might not be torsion free or whatever. But anyway, that's just a sort of another point. If we take all that and say there's something true to that, there's something that is useful there, then I think the natural continuation is to say, well, maybe you have honest hypergraphs, not just graphs. So you still have to play this game, right? You still have to make the notions fit, because actual manifolds have more than paths. I mean, if you think of a graph, 2 graph as a model for a manifold, it's almost like saying that your manifold is a piecewise one-dimensional manifold, right? Because mean, in fact, you can only do paths, and only paths are submanifolds, right? There's no notion of saying that you have three edges, sorry, three vertices belong to the same edge or something, right? That would be like saying that you have a surface, you have a triangle in your space, right? Which is to say that there's space between 1, 2, and 3, right? There's a chunk of space there. So if you agree on that, then it's clear that we have to contend with the fact that we need to travel through these things, and we need to visit edges and so on. And I think that the only thing that really happens here is that we depart from a graph on graph kind of computation to a hypergraphs on the base hypergraph kind of computation. But otherwise, I think we are still in business. I think we are still we have effectively the line graph of these hypergraphs, and we can just play the same game as we were playing before. So a vector field will no longer be like an actual subgraph of the tangent bundle seen as this sort of a directed graph induced by the undirected graph. And this in a way might fix the. In fact, let me see if it does. When we had the problem that it was not obvious how to represent the source, we could represent the sink in sort of this vector field analogy, the discrete analogy, but a source was unclear because I mean, there was no notion of anything coming out of a place that discretely is only mapping to itself, right? So the fact that now you have the between points of the vertices might give you some flexibility to make these notions a bit more fleshed out. But anyway,
I mean,
yeah.
Given that, and it's, I guess, sort of slightly returning to Uti's point from earlier that I dismissed unfairly, but we should revisit, which is exactly what you're talking about, Carlos, right? It's this view of, in the base hypergraph case, in the non-path case, interpreting T as a kind of as the point in between 1, 2, 3, right, in the center of the disk, as Uti put it, right?
Yeah.
So in the same way as I was proposing for path continuity, you can do a similar thing, right? Like, so based on the finite differences between 1 and 3, 3 and 2, 2 and 1, there's a class of, if you imagine now an analytic function that's operating on that polygon, in this case on that triangle, with those as its boundary values, there is a class of possible values for the point in the center if you assume that that function is once differentiable, twice differentiable, etc. And those classes give you essentially ranges of consistent T values. Right?
But what metric do you use? How do you measure distance there? Like
that's a good question. I mean, so I guess what Uti was proposing was that we just interpret these as being ball. We interpret these as being balls, right?
Right. So distance 1, right, or something.
Right.
Yeah.
Right.
Okay. Yeah. And so you take some model. That's neat because in a way it's almost like taking. Actually, I just suddenly lit up something interesting in my mind. Okay.
Yeah. No,
yeah.
I think that actually makes some intuitive sense, right? You say, okay, so like our largest finite difference here is 2. And so, I'm omitting some multiplicative constants or whatever, right? But, so if the value in the center is within distance 2 of, one of the values at the boundary, then it's kind of class, then it's the most smooth. If it's within distance, whatever, 4, then it's, the next most smooth, etc.
Right.
I thought there was going to be no restriction, like you can have any value.
Well, of course, yeah, but the point is that the what value you could choose T to be 1,000, but the point is that the analytic, if you now imagine that triangle is defining is defining a ball with the boundary values of 1, 2, and 3, then an analytic function that's going to assign a value of 1,000 to the center is going to involve very large, is going to involve very high order derivatives.
Right. Oh, okay.
Right.
So
Interesting.
so just like with standard smoothness, the lower the order of derivative you can get away with, the more smooth we say that the assignment is.
You could also have t be 0 and like a bunch of wiggles in between.
Right. But it's
So this is basically the ternary hyper-H is like 2 orders of expansion in that Taylor series, right? The more order you take, the more orders of derivatives you consider.
I suppose, yes.
Well, that's one way to see it. The other way that I'm coming up, which is actually philosophically or morally very close to what you suggested, Nick, that edges are neighborhoods, right? They are somehow points with a neighborhood around it, right? And the vertices are the overlaps. What I like about that in this context is that, I mean, we are finding the need now to assign some kind of metric structure to the edges themselves, so that we can say, if the value of the function is kind of some, conceptually the point in the middle, right, either in the barycenter of the polytope or in the center of a circle, if you think of it as a circle in the end or something, or a disk or something, then I would say that you probably want to have something like you have a model metric space on which you are mapping your edges, right? I mean, this is not literally true, but you're, at least for definitional purposes, right? You might imagine that, each one edge is a point, so that's it. Nothing to discuss there. But each two edge looks like the interval 1, or -1 to 1 or 0 1 or something. Each each 3 edge looks like the simplex, defined in the plane or something, right? Like, and then you think of the metric structure of the ambient space of those simplices for the edges as defining the constraints, right? I mean, that's a possibility, because that just maps a metric structure directly on edges, right? So you have so effectively just take your canonical n simplex embedded in Rn, right? Or n+1, I guess. And then that's a metric space, right? The simplex as the set is a metric space. And now just consider the barycenter of that, and just take your hyper just literally mapped over to that metric space to come up with the continuity conditions. I mean, this is just formalize the notion that you've been saying, Jonathan. It's not going to constrain, right? Because many functions are going to exist in different classes of differentiability or continuity or whatever. But it's going to give a formal statement of that idea, right? It's going to say that you're mapping each edge to a metric space, and therefore there's an edge-wise metric structure that, by metric here, I mean metric space, not like geometric metric. But yeah, I think that begins to look like something that can be formalized and be defined. Yeah.
What would be like interesting, just in terms of finite differences? Oh, wait, sorry.
Yeah.
Did I interrupt someone?
Not me.
Okay. Okay. Anyway, so what would be
It's a
interesting?
pointed question, that's all.
Okay. What would be interesting is like you have, okay, so just to clarify, x, y over here, just as we derive the finite difference constraint for t, we should be able to do the same thing for x, y, and c, right?
Yeah. Yeah.
Okay. So what would be interesting to see would be like, if I have, let's say I'm trying to figure out like the limit of some complete graph. So I start with, like the n complete graphs, in the space I'm getting is by growing all these complete graphs, right? I would imagine that a complete graph would give more constraints. So like it should limit, the things that it can limit to are very less. Like some retractable space or something like that. So what would be interesting is to like just show how how the constraints would like grow, and if we want like a nice map between the constraints themselves, how should the thing grow in the first place? Because how we define, like we can like get one complete graph to the other in different ways. So we can insert the extra point at different places. So the idea should be to to get the same set of constraints for n. There should be a form of the constraints for n, and growing a graph should depend on how to preserve that form of constraints. Yeah, that was fine.
I agree, but potentially worth exploring to the extent that I understand. Do we want to conclude with some rewriting stuff?
Oh yeah. Actually, that might because it's been 2 hours already. So let's
let's not run for too much longer. But let's
Well, thanks for the for help with the nagging thoughts of discrete continuity, as contradictory as it sounds. Okay, so basically, this was my proposal to your conversation with Jonathan's conversation with Stephen when we're talking about adding vectors and composing vectors and things like that, right? Because if I remember correctly, I mean, I don't recall exactly what the issue was, but I think was it the case that you had to basically create some additional vertices to do additions for parallel transport and things like that? Do I remember this correctly?
I can't remember. There were various issues that came up. I think the one that's probably yes. I think that's more or less right.
Right.
To have a sensible notion of parallel transport.
Right.
Like at least with the approaches we were trying, you ended up having to create kind of spurious vertices.
Right. Anyway, so just to have a context, there were some limitations. There were some difficulties in making some notions work, from usual vector calculus and manifolds to our discrete setting. So my proposal was basically to, we are at the Wolfram Institute. We should be the first ones to recognize that, whenever you can do hypergraph rewriting, we should, right? So it's like taking hypergraph rewriting seriously in this context, in my opinion, basically solves the problem of vector calculus or infra-vector calculus or vector infra-calculus, whatever we want to call it. In a fairly trivial sense, in that, if you really are saying that your graphic data is all the data that you have, then any operation, any calculus on this data will be some kind of hypergraph rewriting. Even if you don't phrase it as rewriting, right? You will effectively be manipulating hypergraphic data on a structure, and it will be changing if it's something like algebra, right? So that's the philosophical approach. Now, the concrete approach is how do we do the actual operations that we deal with in differential geometry in the context that we were thinking about. So it is clear that vector field composition is defined by this rule, right? By the way, this is using the hypergraph pack, which I'm not going to run locally now because something's going to blow up because my computer is set so that you have to run it twice, and it crashes the first time. The second time, everything is fine. So I didn't run it once in this particular session, but these are actual rewrite rules. I could apply them to these are labeled rewrite rules. I could apply them to actual graphs if I wanted to. So vector field composition is actually what Uti was talking about earlier. That you have a vector field as a finite difference operator, and this corresponds to a homomorphism, which from the theorem that we said actually corresponds to a mapping, an endomap of the vertices, right? So when you have two of such things, composition of vector fields is just composition of arrows in this sense. It's almost like categorical composition. There's no distinction there. Okay, so that one is very obvious. Now, the not so obvious one is what does it mean to add vectors, right? This is the point-wise addition that happens at every point in a manifold, right? And you do it, tangent space per tangent space, and then you patch it together because every point is independent from every other point. So in our context, I think that what you do is you look at addition as it comes from fine geometry, and you say, okay, what is addition? addition actually is the parallelogram rule, right? It is the fact that you can construct a parallelogram, and in fact, you will see several reformulations of affine geometry, which basically just take the parallelogram construction as the fundamental entity, and then they build out affine geometry out of the parallelogram rule. So, in my opinion, a parallelogram in a graph, right, is when this right-hand side, left-hand side happens, right? You have x and y in this particular configuration, and so you can rewrite the x plus y, which is the long diagonal, so to speak, and or you can do the y minus x, which is the short diagonal, so to speak, right? So plus and minus are again just partially defined as rewrite rules and so on. And so what Nick and I were, and similarly maybe vector field reversal, which you might want to think as minus x, which is a very trivial, just reversing the actual directed edge that corresponds to the vector. So bear in mind that these are rewrite rules in the usual rewriting sense, right? So they are nothing like operations in general, right? They might become operations when these things are globally defined, blah blah blah, and all these nice conditions. But you know, being total in the algebraic sense, I think is way too strong. Certainly for us, you know, we are the champions of rewriting and hypergraphs, and so we shouldn't care about our structures not being total algebraically, which was one of the problems that we had when we discussed with Stephen. So Nick and I were actually discussing that it is neat that in some regime where you have vector fields that in the domain where these operations, in the domain in which these rewriting rules define operations, that is to say, restrict to all the matching subsets or subgraphs for these rules, and then do what I call the one-pass rewriting. A one-pass rewriting means that you take your rule that you apply, you take your hypergraph, and you basically match in all the possible left-hand side pattern matches, right? In all the subgraphs that match your left-hand side, and you rewrite the outcome of that rule application on an empty hypergraph on the same vertices, right? And you accumulate all the possible outcomes. That's what I call the one-pass rewriting. Why is this one-pass rewriting important? Well, that's how you make the actual correspondence between graph rewriting and matrix multiplication of the adjacency matrices, right? So in order to make in what you might ask, in what sense is matrix multiplication sort of the algebraic dual to the graph operation that means to compose the graphs, right? So the specific construction for that correspondence to happen is that algebraically you take your adjacency matrices, you multiply them algebraically, and you get a new matrix. That's the adjacency matrix of some graph, and you have a graph. But graphically, what you say is you have this operation, and what you do is you apply it to all possible matching locations, and you only keep the output of those matches, of those rules applications, and you accumulate them in an empty hypergraph, right? That hypergraph that results from that finite algorithm is exactly taking the product of the adjacency matrices, right? So anyway, so operating under those conditions, you can actually check some nice properties like the zero vector field might make sense to be the one that assigns a self loop everywhere, and so you have nice things like x minus x is the zero vector field, or that the x composed with minus x is just like things coming to the same place, so it's again the zero vector field. So there are some nice algebraic properties that show up in this rewriting perspective that I think is what should be infra-calculus in some sense, right? I mean, infra-calculus is not going to look like calculus, but in a different way. It's going to be something that does not feel like calculus because it's not going to be algebra and doing operations in variables and so on. It's going to be something to do with rewriting, and things are going to be partial and multi-way and so on. But what I think is interesting is that if you do the obvious things with these rules, you're already getting some basic algebraic phenomena that you expect to happen, right? So anyway, this was just to illustrate the motivation on why I think we should take tensor calculus and tensor operations on graphs to be by default given by rewriting rules and be thinking of, doing maybe one pass rewriting constructions to recover actual algebraic operations and then do some kind of interesting matching. But in general, having something that is much more general. Because if you think about this, something that is interesting, but that is divergent from the continuous case is that composition of vector fields is generally not defined. Composition of two derivations is not a derivation, but nonetheless, addition of vector fields is always well defined. And just by looking at the rewriting rules here, it might seem that composition of vector fields is less restrictive in the discrete case than addition of vector fields, because addition requires like 4 vertices and 2 copies of each and whatnot.
And more generally, they are alarmingly similar in this scheme.
Yes.
That the addition and multiplication operation should be almost the same.
Yes.
Yeah.
Yes. So actually, there's also a good reason for that. I was working on that exact problem a little bit this week because there is so what addition of vector fields boils down to vector addition at a point, right, at the tangent space, which itself boils down to addition of vectors on the model space of your manifold, right? So when you think of addition of vectors, it's this kind of conceptual riddle of where you place your origin, right? Like do you think that addition is fundamental, and then the notion of affine space comes from the fact that you have a space with an addition well defined, like an abelian group that maps into some point space? Or do you have a point space that has something like a quadrilateral operation that is this parallelogram construction, and from that parallelogram construction you derive something like an abelian group operation? In my opinion, it makes more sense to think of the geometry. So in my opinion, it makes more sense to think that if you come from an affine space, then this x plus y composition makes sense because x and y always commute, right? So the fact that you can never end up in some other place that is not x plus y, right? You call it x plus y with plus being symmetric, right? Being something that doesn't care about the order, it's an abelian operation. I think that is the essence of affine spaces, right? In a compositional sense. And so if you want to translate that into a completely discrete context where you don't have a model space like you do in continuous geometry, I would say that what you need to abstract is that rule, right? Is the fact that when you have a parallelogram, then there should be a path between them, right? So that's, I think, what is encoded in this particular rewrite rule, which is different from this one, because this one only assumes that there's a corner of the parallelogram and then there's a composition. So it's a weaker requirement. The other one is that there are parallel paths to compose into the same one, and then you compose it, right? So by the way, in this case, if there's 1, 2, 3, 4, and there's x, y composed in the other, you would get 2 different edges here, right? You would get the path from 1 to 3 via 2 will be one edge, and the path to 1 to 3 via 4 will be another edge, because the labels will be distinct, right? Because they are labeled by the vertices in particular. But that would not be the case in the addition case. In the addition case, if you have that pattern, the entire quadrilateral is matched, and you only rewrite a single path between the two, which is kind of representing the fact that the addition of vectors is commutative, if you want. But anyway, I think this is I don't know, more rational way to approach these kinds of things. And to be honest, whenever I heard Stephen say infra-calculus, I always thought it would end up looking like something like this, that involves rewrite rules and is sort of partially defined and is sort of like seeking for pattern matching and things like that, because there's nothing else to do in some sense. I mean, we don't have, you can't force the algebra on it, because obviously then you end up doing like weird things and very artificial things, right? So it's just more fuel to the engine of the rewriting hype, right? It's, I think, preliminarily.
Yeah, it's looking good. And sorry, just so I understand the addition rule properly. So
Yeah.
Is this a general principle that we're expecting to hold, that when we have, if you have two directed edges that are both emanating, one from the source of a directed edge and one from the target of the same directed edge, that we should consider those to be parallel? Is that kind of a general construction that we expect to hold?
Okay, so here's the thing that I mentioned that rewriting suggests about this hypergraph or this path hypergraph and so on, right? In order for these arguments to work, so these nice results like x minus x equals 0 and things like that, you actually need to operate in a symbolic hypergraph. And by symbolic, I mean that the edges need to be labeled by or colored by something that identifies different vector fields. I mean, this is obvious, right? Because if you want to distinguish two vector fields on the same graph, we already had to say, you know, which edge is for which vector field. That's nothing new. But my suspicion is that this kind of algebra that is more symbolic, so that reduces algebraic operations to rewriting rules, this is probably happening in the domain of the path hypergraph, or whatever we call the tangent hypergraph, or whatever that is, right? So that you are effectively doing the hypergraph analog of the path groupoid, right? So you are doing, we are not going to compose, we cannot compose, we are hypergraph, discrete data, blah, 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 partially defined, all that stuff. But we might still have our way of composition, our generalized notion of compositionality, which is having this battery of rewrite rules, and we're going to proceed to just match whatever they match and transform the graphs partially and so on. So all that game, I think, happens on some kind of additional hypergraph on top of the base hypergraph that is further labeled by whatever structures you're considering. So if you're considering a vector field, that's going to be something like directed edges on such hypergraph and so on. So answering your question, there's no statement here in some sense. It's not that I'm making a statement. It's not that I think there should be something that should happen, but it's more like if the notion of a vector field is going to be something like a distribution of directed edges, like we said, like for the past few weeks, to me, it makes a lot of sense, and some preliminary checks suggest that it is sensible, that something like addition, which is generally defined pointwise in manifolds and so on, in our context should be replaced by this particular rewrite rule, which in some sense is like saying this is going to detect in what parts of your space you can effectively consider that locally your space looks like an affine space, right? If you think about it, because you look at 1, 2, 3, 4 in that diagram, that is basically telling you, right? So if you forget about the rest of the universe here, I can actually assume that the 3 can be reached no matter if I go by a 2 or by a 4. So I'm going to, rewrite the green edge to indicate there's an abelian path from 1 to 3, right? So it's just a local property of this particular diagram, right? So whenever that diagram happens, so obviously this will also allow you to identify like entire subgraphs, sub-hypergraphs that are like affine. So like this is an affine region of your hypergraph because all the vector fields defined in this area have a well-defined addition, right? And it actually, the one pass rewriting operation that I mentioned actually defines an honest algebraic operation of addition of those local vector fields, and you can prove that it's actually abelian and so on, which by the way is the same thing as you normally do for matrices, the adjacency matrix. You prove that this is an associative operation when defined for all the graphs and so on. It's the same kind of gymnastics, right? It's the same kind of game. And I'm actually kind of excited because apart from adjacency matrices of graphs and sort of the network theoretic approach of this kind of thing, I didn't have a good motivation to think of hypergraph rewriting as a sort of a proxy for algebraic composition until this, basically, until we wanted to understand what it means to add vectors in a purely intrinsic discrete way, right? We don't use any spurious information. So anyway, I think it's really cool. I'm still early days to see how exactly to implement. But the good thing is that because this is already implemented in the hypergraph packlet, we can actually run some experiments. We can just generate some hypergraphs and generate some vector fields and just visualize what the addition is and so on. And you know, Stephen said, you know, if you had a grid, all these questions that he had, right? Like when you have a grid, it's obvious what it means to have vector fields and so on. Indeed, if you have a grid, then this pattern is exactly what you expect, right? You have the two sort of x, y vector fields being the sort of coordinate vector fields in your grid. And so this rewrite rule applies exactly so that you compose the diagonals, right? And so, yeah, you can go back and forth the x plus y and y minus x, and you can, you know, rewrite back and forth if you have a grid and you have this sort of self-dual property in this particular case and things like that, right? So, you know, these are already operable, right? It's not just a sketch. It's it can be used to check things that, yeah. Anyway, I think that's, but it complicates the picture a bit with when you consider the edges as places, because I think those vertices, although you might be thinking of them as vertices of the base hypergraph, it might be that they are vertices of the line graph of the base hypergraph, meaning they are the places of your hypergraph space, right? But that might be a sort of a subtlety that we work out in the next few days. But yeah.
Yeah, that's looking good. I don't particularly want to think about what happens in the hierarchy case when these rules are being applied to the to the path hypergraph or whatever we're calling it. But yeah, no. So, I mean, certainly in the base case, this looks like it works, right?
Yeah. Yeah. I mean, I think in the higher order case, as I said, it's almost like you forget. Like you can look at your base hypergraph as having connectivity information, but connectivity information is more than place information, right? Place is just the names of the toponymy of your manifold, right? So the names of the places where you can go.
Right.
And so if you just have that, that is your new vertex set for the hypergraph that we're talking about, this sort of path hypergraph, right?
Sure, but in the case where, say, x and y are hyperedges, do you take 1 and 2 to just be the endpoints, and you kind of if it's a directed hyperedge and you ignore everything that's inside, or can you kind of add 2 vectors sort of at any intermediate point, if that makes sense?
I would say so. Yeah. I mean, as long as it's matching this pattern, right? In the if the vertices are names for places, right? Then I mean, the name place is meant to be evocative precisely for that. Yeah.
I think basically they don't have to be hyperedges, right?
No, they don't have to be
Your
hyperedges.
vertices here are places, they were hyperedges, and edges here on this dual of it basically only indicate the incidence between them.
Yeah.
So
right. Yeah, that's kind of what I'm clarifying.
Sure.
So I should think of the x and the y here as just being a specification that these 2 places exist in the same hyperedge or something.
Well, what I would say is that so x and y here are directed edges of the place hyperedge. Sorry, of the place hypergraph, right? So they are directed edges. Sorry, they are directed edges of the line graph of the place hypergraph, right? So this means it's simpler than it seems. It's simply you have your base hypergraph. Each edge is going to have some name, right? Some label, whatever it is. Think of it as the numbers 1, 2, 3, 4, right? So these diagrams are diagrams of paths because they only involve directed edges. They are rules that apply to paths, right? So it's like infinitesimal paths. So that's why we call them vectors, because they are length 1 paths, right? So they are statements about how you move between places. So here 1, 2, 3, 4 could be, you know, in this whatever diagram that I had up here, this could be like, you know, the edge 1, 2 between 1 and 2, the 1, 2, 3 triangle in the middle, like any of the edges of this hypergraph could be one of the vertices of these rule applications, right? So being parallel means that, you know, if you can go from, you know, 1 to t, or let me use the labels, you know, x to t and you know, c to y, and you know, you have 2 parallel vectors that go there, then you can go the other way. Is this kind of statement, right? It's which, if you're taking to heart the meaning that if the places have different labels, then they're really sort of physically different places in some sense, then the rule, this parallelogram rule still makes sense, right? Because it's saying that in that regime of your hypergraph, there's some degree of a fineness, right, in that regime, that, you know, which is absolutely not global in general, but yeah, I think that's what I wanted to say, by the way, in the very beginning, that you I mean, it seems obvious that we have to create this path hypergraph or this additional hypergraphs on top of the base one to make sense of notions, as you said, like paths, and then maybe try to think about convergence and properties of, you know, accumulation points and things like that. But I think this is another justification of why we need such a sort of additional or virtual hypergraphs on top of the original one, because these rewrite rules only really make sense when you're considering abstract names for places, right? Not literal edges of, like, because I mean, it can be that you're what sense does it make to actually rewrite the tangent bundle of a manifold, right? When you add two vector fields, the tangent bundle doesn't change. It's the two, you have a vector field, another vector field, and you relate to a third vector field that is the addition, but you're not transforming the tangent bundle by doing that, right? So that's why it would be weird that these rules apply to the base hypergraph somehow, right? They should apply to some kind of added structure on top, and which is symbolic, it's labeled, and so on, and you know.
Sure. And I like Nick's intuition of thinking of these infra-calculus rules as essentially acting on an incidence structure that's defined over the hypergraph rather than, yeah.
Exactly. Yeah, that's right. That's right. Yeah, I think that was about the ideas that I wanted to share 2.5 hours later.
Well, thanks a lot for that, Carlos, and thanks Uti and Nick for filling in details. And yeah, I'm sorry it took that long, but I think, I don't know, I think I understand things better than I did before we started. Maybe it's worth us having a more detailed. So maybe it's worth us kind of. I'll think about this a bit, but maybe it's worth us having another conversation, possibly live streamed, in which we try and work out these details of, you know, precisely what these what these continuity constraints should be, right? Like what exactly should be the relationship in both the base hypergraph and in the path hypergraph. What is the relationship between kind of differentiability classes and, you know, constraints on these, you know, these field assignments to hyperedges.
Yep.
I feel like we've got something that's with some combination of these ideas. I think with this notion that you should think of each simplex as essentially having some canonical map to a metric space, and then say, you know, we define a function over that metric space, and we essentially ask, you know, how high do we have to go in the derivatives of that function before we get something that's compatible with the value we assigned? I think some combination of those ideas we should be able to write, a concrete piece of code that just determines, you know, for a given assignment, determines the continuity class for that assignment. So I think it'd be nice to do maybe another live stream meeting where we actually try and do that.
Yeah, that sounds very reasonable, and yeah, I'll personally work on trying to get some nice examples of the geometry of this rewriting perspective, because it's been a while since I found any application for this philosophy. Before it was just pure algebra, but now it's like, all right, so maybe, you know, representing the partial nature of discrete geometry might be another avenue for the application of this philosophy. And it's great.
Yeah, that's very exciting.
All right, everyone, thank you so much. We have a lively conversation going on the YouTube channel here.
Yeah, do we have, just before we leave, do we have any addressable questions?
Let me see. Some mention about geometric algebra, talking about density of edges. I asked what they mean by density of edges.
I mean, this is maybe a silly crackpotty comment, but you know, there's something rather this construction, you know, this whole edges as places idea. There is something inherently quite geometric algebra-y about that, right? That's, you know, that somehow, you know, when you go from, you know, when we say, okay, I have some collection, I have a K-blade, I have some collection of vectors, and I'm going to treat that as being, you know, I'm going to treat each of those as being the vector in some higher space. But if you compare that to what we're doing, where we're essentially saying, I have some sequence of places in the general sense, and but there's some way I can treat that sequence as being a single place in some higher order hypergraph.
Yep.
It's something, I don't know, somewhat thematically analogous there.
I think it's, sorry, Jonathan, I think the analogy is not only thematic, I think it's very close to what is happening, right? Because to me, geometric algebra is a way to package all this tangent information, right? All the tangent bundle information, the higher order sort of what I like to call the orientable tangent elements, right? With blades, right? Like you have vectors and bivectors, multivectors, and combinations of such things. So that is precisely, if you take, instead of just thinking of literal paths, which are, sequences of directed edges, or you take oriented subsets, right? And as generalizations of paths like oriented surfaces and oriented polygons and things like that, then you end up with essentially the same idea of developing from a base hypergraph, developing this higher hypergraph. And the moment you assign some notion of, for example, angle, like we said last time, could be that notion could still make sense, right? Where we had this binary angle, discrete angle between elements. Then I would say that virtual hypergraph, this hypergraph of oriented shapes, oriented paths, or whatever, becomes effectively the discrete analog of the geometric algebra of a manifold with a metric structure, right? I mean, obviously that's just those are just words, but if we believe ourselves in this kind of message that we're giving out, that there's a discrete notion of geometry that is formally analogous and so on, that would be the literal geometric algebra analog. It won't be just like kind of similar, but it would correspond to that, because curves correspond to tangent vectors in the same way that oriented submanifolds correspond to tangent blades in some sense, right? So yeah, it would be very literal with that. So yeah, it's very good.
Right. And I think it's a nice intuition to think about this construction of higher places from kind of lower objects, right?
Yeah.
To think of that as being kind of our analog of an exterior product, I guess, sort of makes sense, right?
Yeah. No, that would be very interesting actually, because I mean, I have an immediate intuition for what an interior product should be in our context, which is precisely, you draw the diagram that it's in the textbook, right? But you make it into a rewrite rule. So it's almost like, I don't know any maths. I just go to the textbook, look at the picture like children, and like just copy it in the rewrite rule. But I mean, that's I think what it would be like. You have two vectors, and either you say, yeah, two vectors map to a ternary edge, right? An oriented ternary edge, and that's taking a wedge product basically of those two vectors, right? So yeah. It's very literal, right? So the moment you depart from order RET2 of your edges, right? You are effectively doing this wedge product operation if you are directed, right? So yeah. Anyway, I think it's very exciting. I think we are onto something here, hopefully.
Let's hope so.
All right, everyone. So thank you so much for the chat here and on the live stream. Thanks for all your comments. I will share, I don't want this conversation to die off because it's indeed quite lively. We have a nice viewership, and I want to share our community link so everyone can join our Discord, where lately we've been having some nice conversations as well. So I'll share the link right now on the YouTube. So make sure to follow that link. You can keep up to date from the Twitter accounts, the Institute and the Wolfram Physics one, for things that are relevant there. And yeah, thank you so much. And you guys, I will see you next week.
Thanks, everyone.
Thank you, everyone.
Goodbye. Thank you.